So we continue today with Fourier transform, and we start Fourier sine and cosine transform. So just to remind you, because this is our motivation, to remind you what was the Fourier transform. Remember, if you have a function that's integrable, this is the notation for integrable functions, then the Fourier transform is defined by f hat of omega equals 1 over root 2 pi integral from minus infinity to infinity f of x e to the minus I omega x dx. And the inversion formula for the Fourier transform is if the Fourier transform itself is integrable, then we can go back from the transform to the function by the inversion formula f of x equals almost the same integral. And we mentioned many times in our classes that this f of x, although we write it f of x for simplicity and to look at it as an inversion formula, what we mean basically by f of x is the limit from right plus the limit from left over 2. So in case the function was continuous, this is equal to the function f of x. Now I like to go back to Fourier series and just remember the main topics in Fourier series. We started Fourier series, so just like make a little comparison just to see where we are going. So we had Fourier series, then we have the transform. In Fourier series, we had the definition of the Fourier series. Then we had the definition of the Fourier series. In fact, we had the definition of the Fourier coefficients, the an, the bn, the cn. Here we have the definition of half of omega. Then in Fourier series, we had the definition of the inversion formula. In fact, the inversion formula in the Fourier series is the Fourier series itself. Then we had the inversion formula, which is just this one in the Fourier transform. After that, in Fourier series, we dealt with what's called Parseval's identity. And in the Fourier transform, if you remember, we did the Parseval identity, but usually it's called the Plancherel theorem or Plancherel identity. Then in Fourier series, we studied what happens if the function was odd or even. Remember, if the function is odd, we see only a series composed of sines, and if the function is even, we see the constant together with cosine. Now, with the same alignment, we are going to see what happens if the function is even or odd in case we're dealing with the Fourier transform. So just keep this comparison in mind, how the two concepts are going parallel in the same way. Okay, so we want to see now what happens if the function f is even, for example. So if the function f is even, what is f hat of omega? It's 1 over root 2 pi integral from minus infinity to infinity f of x. This is the definition again. We have not added anything. But now, what is the e? The e to the I wx, this is neither odd nor even, but we can write it in terms of the cosine and sine. So now this is cosine omega x minus I sine omega x dx. And now recalling that this function is odd, this function is even. So now in my assumption, if the function, if this f was even, when you multiply these brackets, when you expand the brackets, what you will have is 1 over 2 pi integral from negative infinity to infinity. F of x is even times the cosine is even. But then when you multiply the f with the sine, so when you expand the brackets and you multiply this with this, the function is even, the sine is odd. When you multiply them, you get an odd function, and the integral of an odd function is 0 from negative infinity to infinity. So basically this is what we are left with. And because the function is even and the cosine is even, this integral is double from 0 to infinity. So this is what happens if the function is even, then the Fourier transform is equal to this. On the other hand, if the function was odd, what is f hat of omega? F hat of omega is going to be, this is the definition again, so we go back to this line, but this time if the function was odd, when you multiply the odd with the even, the result is odd, and this is what's becoming 0, but then when you multiply the odd with the odd, you get even. So in this case, what's left is basically the sine term, not the cosine term. So if the function is odd, so the conclusion now, if the function is odd, what we will get is 2 over pi, yes, from 0 to infinity, minus I f of x sine omega x dx. Remember, all the time we can play with the constants, so we don't like seeing the negative I. And this argument here, what you're seeing now on the screen, the even and odd cases, this is the trigger and the motivation behind the definition of our title. Our title was the Fourier sine and cosine transform. So now I'm going to write the definitions. So if f, and now, because if you look at the integrals in the end, if the function is even, remember what we mean by even and odd functions is that you have a function, for example, if you talk about even function, it's a function that's defined on the whole real line, on the right and on the left, but it's symmetric about the y-axis. So basically, if you know the right part, if this is your right part, then just by symmetry you can draw the left part. So basically, when you talk about an even or an odd function, knowing the right part only is enough, because then you can describe the left part. That's why when we talk about the cosine and sine transforms, we will not take functions defined on the whole real line. Rather, we take functions defined on the interval 0 infinity. So if you have a function defined on 0 infinity to r, if it's an L1 function, so the integral of the absolute value of the function is finite, and this is very important to guarantee the convergence of the improper integral. Otherwise, the integral does not exist, and we can't talk about these transforms. So if this is L1, then the Fourier cosine transform is what? Is f hat of omega. It's exactly this thing, okay? It is exactly this thing. So this is root 2 over pi integral from 0 to infinity f of x cosine omega x dx. But this is a little bit confusing because we used the notation f hat of omega for the Fourier transform itself. So now to distinguish this from the Fourier transform, we're going to write sub c here, okay? So this is f hat sub c to indicate that we are talking about the Fourier cosine transform. On the other hand, the Fourier sine transform is what? It is f hat s of omega equals this. So we have very similar definitions. This is the cosine transform, this is the sine transform. They are very similar. And again, why did we have these formulas specifically for these transforms? Because this is what we got when we talked about the even and odd cases here. This is the analysis behind the two definitions. In fact, not only this, but also if these transforms are in L1, then we can talk about the inversion formula. So again, what is the inversion formula? The inversion formula is about going back from the transform to the original function. So in these boxes, if you look at these boxes, so if you give me the function, I integrate it, of course, against the cosine, we get the cosine transform. But what about if I give you the Fourier cosine transform? How do you go back to the function? This is exactly what we mean by the inversion formula. It's very easy to memorize these formulas because of the symmetry. So basically, we have almost the same definition. If you compare the cosine transform, this formula, with the inversion form of it, they are identical, except for having, sorry, this one is, I always do this mistake, this is the omega. And the same thing if you look at the inversion formula for the sine transform. And again, we remember we don't mean f of x, we mean f of x plus f of x minus over 2. But again, it is a habit that we write f of x, and it is f of x if the function was continuous. Okay, so this is our definition for the Fourier cosine and sine transform. Let's see some examples. So for example, if we take the function f of x equal e to the minus x, and remember, when we talk about the Fourier cosine and sine transform, the interval is from 0 to infinity. And is the 0 included or not, we don't care. Points do not change anything. But the functions are not defined on the whole real line. So if the function is e to the minus x, of course, when x is positive, let's compute together the cosine transform. So what is the Fourier cosine transform of this function? It's the integral. Sorry, it is the integral. We have root 2 pi as a constant from 0 to infinity, the function times the cosine. And this is root 2 over pi. So now we need to do the integral e to the minus x cosine x omega dx. And this will be 1 over 1 plus omega squared. So if you do this integral, unfortunately you need to do it integration by parts, then you will reach this formula. However, we will see later how to obtain this formula without doing the integral, okay? We will see it. What is the sine transform? So again, we have this root from 0 to infinity, e to the minus x sine x omega dx. If we do this, it will be omega over omega squared plus 1, okay? Again, we need to do it by parts, and we will see later how to do it easily. Okay, so these are the Fourier sine and cosine transform. What about the meaning of the inversion formula? So what is the application of the inversion formula? So now if you look at in this example, f hat sub c, the Fourier cosine transform, it is in L1, so I can apply the inversion formula. What does the inversion formula say? It says f of x, and again, f of x, we mean f of x plus f of x minus over 2. This is root 2 over pi integral from 0 to infinity, the cosine transform times the cosine itself, dw. So this is, if you substitute, what is fc hat? We just found it. It is this quantity, which is 2 over pi integral from 0 to infinity cosine wx over w squared plus 1 dw. Okay, so what we found basically is this. We found that 2 over pi, the integral, and this is one of the most interesting applications, mathematical applications, let's see, for the inversion formulas. So this is what we've got. It's equal to f of x, but again, when we say it's equal to f of x, we mean the limits from left, from right over 2. So what is my function? In this example, my function is e to the minus x. So if you draw e to the minus x, this is it. When you talk about the Fourier cosine transform, that means you are looking at this function as an even function. So in case you need the left part of the function, this is it. This is the extension of this function to an even function. So is the function continuous? Yes, it is continuous. So in this case, what is this integral equal to? It's equal to the function. So if you take the limit from left, from right over 2, it will be exactly equal to the function, and this gives you a very nice integral, which is cosine wx over w squared plus 1 dw is equal to pi over 2 e to the minus x. This is a very nice integral. For example, if you plug x 0, what do you get? This integral becomes the integral cosine 0 is 1 plus omega squared d omega is equal to pi over 2. And this is, by the way, this is a very easy integral. By calculus, this is tan inverse. If you substitute infinity and 0, you get pi over 2. But if you substitute, for example, x equals 1, what do you get? The integral is from 0 to infinity cosine omega over omega squared plus 1 d omega is equal to pi over 2 e to the negative 1. This is a very nice integral. It cannot be computed using any of the known integration techniques like the calculus techniques. To do this integral, the only ways, by the way, to do this integral is to use symmetric methods like the Fourier, like what we are doing right now, the Fourier cosine transform. We did this integral using the inversion formula for the Fourier transform itself. So we need always to use symmetric methods to compute these integrals. There is no calculus technique to find these integrals. This is one big benefit of these inversion formulas. Okay, let's see another example. For example, let's take the function 1 if 0 is less than x less than 1, 0 otherwise. And please, when we talk about, so let's find the Fourier cosine and the Fourier sine transform. Whenever we talk about these Fourier cosine and sine transforms, the interval of the function, the domain of the function, is from 0 to infinity. So here when we say otherwise, we don't mean the negative numbers, we mean the positive numbers that are not included in the first interval from 0 to 1. So again, we just have the definition. So what is the Fourier cosine transform? It's root over 2 pi integral the function times the cosine, which is the integral from 0 to 1 times the cosine, because otherwise the value of the integral is 0. And this is an easy integral. The integral of cosine is just sine over omega from 0 to 1. And nicely, if you substitute the 1, you get sine omega over omega. If you substitute the 0, you get 0. So the Fourier cosine transform of this function is equal to this. What about the Fourier sine transform? So the Fourier sine transform is equal to the same thing, but the integral from 0 to 1 times the sine. It's the same computations exactly, which is the root. So what is the integral of sine? It's negative cosine over w negative. So I'm going just to write, instead of writing negative, just to flip the limits. And if you substitute now, what you're having is 1 minus cosine omega over omega. So this is the Fourier sine transform. Okay. Okay. So that's it. This is how you compute the Fourier sine and the Fourier cosine formulas. Now, if you look at, if you like to compute or to look at the Fourier sine and cosine transforms as new functions. For example, if you look at this function here and you ask this function, the Fourier sine transform, is it an even or an odd function? The same for this thing. Is it an even or an odd function? So basically, if you look at the Fourier cosine transform, it's this constant times this. Basically, this definition applies for omega positive. But if you like to substitute a negative value, you can see that substituting negative omega in this integral is just substituting negative omega into the cosine, and the cosine cancels the negative sign. So basically, you're going to get the same thing as substituting omega, which means that the Fourier cosine transform is an even function. Following the same thing, you can find that the Fourier sine transform is what? It is an odd function, if you like to substitute negative values. Then the other thing that we usually care about in using the Fourier sine and cosine transform is some relations, and you will see why we need these formulas, and we will go back and solve the first example we did today. Remember when we computed the Fourier cosine transform of e to the minus x, we had to do these difficult, let's say, integrals, integration by parts twice and so on. So we have some computations. Now we can adopt some identities that simplify these computations. Remember, for example, when we studied Laplace transform, we had a formula about relating the Laplace transform of the function with the Laplace transform of the function, to relate the Laplace transform of the derivative with the Laplace of the function. And we had a relation like this, if you remember, from the differential equations course. Now we want to look at something like this. So I want to look at if you take the derivative of the function and you try to find the Fourier cosine transform. So I'm going to write it this way. If you want to find the Fourier cosine transform of the derivative, what is it? Or if you want to find the Fourier sine transform of the derivative, what is it? And then how can we use these formulas? So if you have a function, you have the derivative of that function, you want to find the Fourier cosine transform. What is it? It's the integral, right? You have the derivative. This is the definition, so we're not doing anything. So this is 2 pi. And what is this integral? Now the idea is that I want to relate this to the Fourier cosine or maybe the Fourier sine transform of the function. So when you say it of the function, that means you need to have f of x instead of f prime. So I want to look at this f prime and change it to f. To do this, I will need to do it by integration by parts. So I'm choosing f prime as dv, so when you integrate it you get back to f, and the u is going to be the cosine. So when you differentiate this, you get minus sine wx w, sorry, so this is minus w, and when you integrate this you get f, and integration by parts, which gives you, so when you multiply, you get f of x times the cosine plus omega integral f of x times the sine, right? Now the limits of the integral are 0 to infinity, and the limits here are from 0 to infinity. So this is going to be equal to root 2 over pi times, now what is this? You substitute the infinity, so basically you're getting f of infinity cosine infinity w minus, when you substitute the 0, you get f of 0, then plus w, and what is this integral here? What is this integral? It reminds us of the Fourier sine transform with the root 2 pi, so I'm going to write it for the next step. It's all multiplied with root 2 pi. Please remember at this point, writing f of infinity is not completely right. We need to understand what we mean by f of infinity. So when we write f of infinity, what do we mean? We mean the limit as omega or x or b or anything, let me write it, x approaches infinity. This is what we mean. Although we don't write it, this is what's meant by f of infinity. So basically when you look at this term here, what do we mean? We mean the limit as x approaches infinity, f of x cosine omega x, okay? This is what's meant, but we don't need to write it. Remember, this has to be done in Calculus 2 course, but at this level, at this course level, we don't need to write it, but we need to look at it this way, although we don't write it. Okay, so here, what is f of infinity? f of infinity means the limit of the function as x gets larger and larger. So imagine, just imagine, f of infinity, imagine, I'm saying, f of infinity was 5, okay? what is cosine infinity times omega? Omega is just a number. Imagine it 2, for example. So here you're talking about cosine infinity, and cosine infinity, if you draw the cosine function, it keeps oscillating, so the cosine does not exist. So if f of infinity was 5, you multiply 5 with the, I'm talking about this thing, okay? So if you multiply the two quantities, 5 times does not exist, it does not exist. 10 times does not exist, it does not exist. The only way to make this does not exist times f of infinity, the only way to make it exist is to have f of infinity equal 0. This is the only way. And the idea here is, if you look at cosine anything, whether it's infinity or anything, it's always between -1 and 1. So if you multiply all sides with a quantity that is approaching 0, so if this was 0, 0, then by squeeze theorem, this is going to be 0. So at this stage, we say, okay, so for my integral to be valid, to exist, I must have the limit as x approaches infinity, f of x equals 0. So if this limit exists, and is equal to 0, then I can say, okay, this integral, this product here is 0 using a squeeze theorem. So in this case, what is left is negative root 2 over pi f of 0 plus root 2 over pi omega integral. And this is, if you look at the second term first, you have omega and the root with the integral, that the Fourier sine transform of the function, then minus root 2 over pi f of 0. So again, what is this? This is the Fourier cosine of the derivative. So if you have a function, you have its derivative, and you want to find the Fourier cosine of the derivative, then this is exactly what you have. And if you look at this formula, this is very, very similar to the formula we have with the Laplace transform, right? Because the Laplace transform of the derivative is s Laplace of minus f of 0. Of course, the s replaces the w. So the two identities are very similar, just for comparison. Okay. So this is what happens when you find the Fourier cosine of the derivative. And again, we will see after the second identity how we apply this. Let's find the Fourier sine of the derivative. Okay, let's find the Fourier sine of the derivative. So what is the Fourier sine of the derivative? It's root 2 over pi integral the derivative times the sine, which is the root. Now, how do you do this this integral? Again, you do it by parts, but this time the u, the dv, the u is the sine, and the dv is f prime. You integrate this, you differentiate this. Standard steps. Then you do it this way. So if you do the computations, this will be f of x times the sine minus omega integral f of x times the cosine, right? This is from 0 to infinity, and this is from 0 to infinity. Now, if you look at this, root 2 over pi, if you substitute the infinity again, you will get f of infinity the same as before. You will get f of infinity times sine infinity, and that's 0, assuming what? Assuming my assumption here. Okay, so assuming the limit as x approaches infinity, f of x equals 0, then you will have again, so I'm going to write it again, f of x equals 0. Then when you substitute the infinity, you get 0 minus, so if you substitute the infinity, you get 0. But also this time, if you substitute the 0, you get 0. And remember, in the previous case, when you substitute 0, you don't get 0, you get f of 0. That's the difference. So when you see the two formulas, don't ask why are the two formulas different. They are different because of this. If you substitute the 0, you get 0 here, but if you substitute it there, you don't get 0. So now this will be just 0 times minus omega integral and this is minus omega what? This is the Fourier cosine transform of the function. So the Fourier sine of the derivative is equal to this. This is the summary of this remark. Okay, so we had two formulas now. We have two formulas now. One of them is about the Fourier cosine of the derivative. This is it. And the other is about the Fourier sine of the derivative. This is it. Let's see an example. So let's go back to the function f of x equals e to negative x. Okay, so remember this was the first example we did today. This is it. This is the function. We had all the computations hidden somewhere about the Fourier cosine and sine transform. We said to do these integrals we need to do it by parts, but the idea is that we can apply the new identities for the derivative. Let's see how we can do it. So in this case, what is the derivative of the function? The derivative of the function is basically negative e to the minus x, which means f prime is negative f, right? Because f is e to the negative x. So if you want to find the Fourier cosine of the derivative, what was the formula for the Fourier cosine of the derivative? It was the w times the Fourier sine of the function minus root 2 over pi f of 0. Again, what did we do? We just copied this formula here. Okay. So this means, so what is the Fourier cosine of f prime? F prime is just negative f. So this is the Fourier cosine of negative f equals omega Fourier sine of f, right? But f is negative f prime. So I'm just playing with this stuff. And what is f of 0? If you plug 0 into the function, you get 1, right? So this is Fourier cosine negative of f equals, this is w, this is negative, Fourier sine of the derivative minus 2 pi. Okay, now, so this is this. What is the Fourier sine of the derivative? The Fourier sine of the derivative is, this is the formula here. So you just substitute and you get negative omega, the Fourier cosine of the function, right? So what is this? This is w square Fourier cosine minus 2 over pi, and this is minus the Fourier cosine. And at this point, you can say, okay, let's move this term to the side and this term to the other side. So what do you get? You get omega square plus 1 times the Fourier cosine transform is equal to 2 over pi with the root, and that means the Fourier cosine of f is this. And remember, this is exactly what we had before. If you look at the computations for the function e to the minus x here, the Fourier cosine was this. And remember, to do these computations, we had to use integration by parts, where some potential for some errors or mistakes is there. Now with these ideas, with these identities, so if you manipulate these identities, you can reach some formulas and avoid some other computations. On the other hand, so let's say this is 1. If you look at the Fourier sine, so I want to find the Fourier sine transform of this function. So the Fourier sine of the derivative, the formula says the Fourier sine of the derivative is negative omega times the Fourier cosine of the function, right? But I know the derivative is negative the function, that's negative omega, and what's the Fourier cosine? We just found it. It's this, right? So if you take the negative out, then the Fourier sine transform of the function, the negative cancels with the negative, and you have the root omega squared plus 1. And again, we had this before. if we applied integration by parts. So this is how we apply this formula, the Fourier sine of the derivative or the Fourier cosine of the derivative. These are very nice formulas. Then if we look quickly at very simple properties that I think most of you have already observed, is if you look at my computations here, I took this negative out. So this negative, I took it out. This negative here, I took it out. So what justifies this is the following remark. So what is our property? Our property is if you take the Fourier cosine of any number times the function, what is it? It is the root, the definition is the root, integral, the function that you are interested in, which is alpha f in this case, times the cosine. But because the alpha is a constant, you can take it outside the integral, and this is what you are left with. And this is exactly alpha times the Fourier cosine of the function. So this justifies taking the constants outside the Fourier cosine transform, the Fourier sine transform, similarly, the Fourier transform, the Fourier series, all these transforms take the constants out. The other simple property is if you take the Fourier cosine or sine for alpha f plus beta g. So imagine alpha is a constant, beta is a constant. What is this? This will be alpha times the Fourier cosine of the function f plus beta Fourier cosine of the function g. It is very similar to the above one. So if you do just the integral, distribute it, and take the constants out, this is exactly what you're going to get. So this is a summary. I think this is a very detailed summary of the concept of Fourier cosine and sine transform.